Hello everyone, welcome back to CFD College. I'm Ashkan and this is another tutorial about Fluent, ANSYS Fluent. Actually, this tutorial is another session of our beginner to advanced ANSYS Fluent training course. And this is another example, two-dimensional flow. And as you can see, it's flow over a flat plate. We are gonna uh, solve this project, perform this simulation from the scratch in ANSYS Fluent in two situations, laminar and turbulent flow. This tutorial is about solving the project where we have laminar flow, and in the next tutorial we will deal with turbulent flow. And since we have heat transfer, we will have another tutorial after which is related. Uh, uh, in that tutorial, I will teach you how you can calculate Nusselt number in such flows, flow over surfaces. Actually, we can say in how you can calculate the Nusselt number in external flows. So let's jump to the problem statement. This is our CFD domain. As you can see here, we have a flat plate with the length of 20 meters. This is the CFD domain. And we have a rectangle. Uh, the length is 20 meters. The height is 4 meters. It's simple because it's 2D. And this surface represents our plate. As you can see here, and as you know, when we have a flow over a flat plate, we have three regions: laminar flow, transitional flow, and turbulent flow. Until here, where the Reynolds number, the local Reynolds number reaches 100,000, we have laminar flow. Then from critical Reynolds number, around 10 to 5 or 5 times 10 to the power 5, which is considered as critical Reynolds. After that, we have from this Reynolds number to 3 million, we have transitional flow, which is the hardest regime to simulate or even to use experiments. And after that, we have turbulent flow. So in this example, in this tutorial, we deal with the first one, laminar flow, and in the next one, we will have turbulent flow. And in the third tutorial, after those, we have calculating the Nusselt number in external flow. And so, as I mentioned, here we have laminar flow. The length is 20 meters. The air velocity is 0.0735 meters per second. The air temperature is considered as 300 kelvins, and the plate temperature is 400 kelvins. The working fluid is air with density of 1.225 and the viscosity of 1.8 E minus 5. Um, so we have heat transfer, but we don't want to, explain it more in this example in laminar flow. In laminar flow, we will focus on shear stress and skin friction factor. Then in turbulent flow, as I mentioned, we are gonna uh, deal with the temperature, the heat transfer, the Nusselt number, and so on. So some theoretical insights. This is the flow over a flat plate. As you can see, when we have a flow over a flat plate, we have the boundary layer. The boundary layer you saw here, this is the boundary layer actually. This delta represents the height of the boundary layer. And as you can see, it varies at different locations. So we have some, solutions for Navier-Stokes with thousands assumptions. And I think you might have seen these. This formula 5 times x represents the local coordinate, local length of the plate, divided by a square root of Reynolds number at that location will give us the thickness of the boundary layer. And at that point, we can find the friction coefficient by this formula 0.664 over square root of Reynolds number. These formulas are valid in laminar flow. We have similar formulas for turbulent flow. And this is the general, equation for skin friction factor. The wall shear stress divided by 1 over 2 density times velocity squared. So we have this domain, as I mentioned, and we know the velocity and everything. So let's go to Excel file. And just let me, oh, okay, so we have the ANSYS workbench there. So we have a row, we have viscosity, and we have length. Row is 1.225, viscosity is 1.8, E minus 5, length is 20 meters. You know the units. And so the Reynolds number, sorry, we need velocity. Velocity was 0.0735. Yeah. So the Reynolds number equals rho V L over mu, which is 100,000. So we can assume that we have laminar flow. And this is the critical point, but we have laminar flow. And when you want to create your domain, this height is important. So since we have the length of the plate, it's better to calculate the delta, thickness of the boundary layer, to be sure that we have enough space above the boundary layer. So we have the formula 5 times 20 divided by Reynolds number at the edge. So delta equals 5 times length divided by square root of Reynolds. This is meter. So it's 0.32 centimeters. So this height, 4 meters, is enough because the boundary layer should be here somewhere. So we have enough space above the boundary layer to maintain the flow parallel to the outlet. This outlet, not this one. So now we can go to Workbench and perform the simulation. So I will work with Fluid Flow Fluent. And as you know, I'm going to use Design Modeler. This is so easy, so you can use whatever you want, either Space Claim or Design Modeler. As you know, in 2D simulation, we should draw this sketch in XY plane. So 20 meters, 4 meters, surface from a sketch. That's it. Just simple as that. Now I will close it and go to ANSYS Meshing. Okay, now we have ANSYS Meshing. If we wanna generate structured mesh, so we need face meshing. Then we need sizing for these edges. For example, 200. And these ones, 40. And since we wanna capture the boundary layer, I know it's laminar flow, but we still have the boundary layer. So I'm gonna use bias factor of 40. This one should be reversed. Okay. So this is inlet. This is the plate. This is outlet. And I'm gonna use a symmetry boundary condition for this far field boundary. Well, we have the mesh, and let me update it. Now we can close it and go to ANSYS Fluent. Just let me save it. Flat plate is fine because we will have laminar and turbulent flows, both of them in a single workbench. So I will use 4 processors, double precision, always select it, always check it. We need that for the accuracy. So it's not difficult. The settings I mean. Let me. Now it's perfect. So steady simulation, 2D planner. We need energy equation. We need it the end when we wanna calculate the Nusselt number in both laminar and turbulent flow. So here now flow is laminar and the material is air. So this is 1.8, 1.225, and these are okay. Boundary conditions, inlet velocity is 0.0735 and the temperature is 300. That's fine. Outlet is pressure outlet with gauge pressure of 0 because we have atmospheric air there, and the plate is wall with the temperature of 400 kelvins, and this is the symmetry. Okay. Now we have to pay attention to reference values. So the application of reference values is when you wanna export some dimensionless numbers, for example, Nusselt number, like what we wanna use in this simulation, skin friction factor, or any other numbers. See this? Skin friction factor equals to shear stress of the wall, which is calculated by Fluent, divided by 1/2, no problem. Density and the velocity. These two, actually, I think most of the parameters that we have in the denominator of the uh, formula for dimensionless groups and numbers, you can find them in reference values. So that's here. This is the velocity, and this is the density. If you want to calculate Nusselt number, uh, you know, I always use the manual method. I never use ANSYS Fluent to calculate Nusselt number. I will teach you in future tutorials. We will see that for external flow, and I will mm, provide you with another recorded video for calculating Nusselt number in internal flow. And you will, if you see those tutorials, you will understand that the number that Fluent gives you in most of the times is not correct, and you have to use the manual method. But anyways, it's a good idea to select this and choose inlet, compute from inlet in in all of the simulations, because this way the at least the velocity and the temperature will be updated. And this is what we want, the velocity of the free stream, which is 0.0735, which is the velocity we applied at the inlet, and also the density and viscosity. And another issue in 2D simulations or even 3D is this length. The depth of the domain is always one, but the length is the characteristic length of your simulation. We don't need it in this simulation, but you have to pay attention to this. So what's next? Click on this one. Coupled is good. And the residuals, 1, 2, 1, 2, 1, 2. It's simple. And let's initialize and run, for example, 1000 iterations. Let's see. The convergence is good. And as I mentioned, it is converged. But now let's uh, decrease it to 10 to minus, for example, 8 to see if the residuals are straight or not. Now they are decreasing, but it's fine for us. It's actually more than fine. So now the simulation is done. So, okay, how can we get skin friction factor from ANSYS Fluent? Well, there are two different ways. The first one, you can export the shear stress, the wall shear stress, and then calculate the skin friction factor yourself. But the other way is to use XY plot. Click on XY plot. The plate is horizontal, so plot direction is X. And most of the users and students always ask me how I can find the skin friction factor. You have to go to the wall fluxes section, and here you can see wall shear stress X and Y. You can, for example, export this one and manually calculate the skin friction factor. But here, look at here, skin friction coefficient. It's CF that I showed you here. So it's simple. Oops. Select wall fluxes, and under that, skin friction factor, select plate, and plot it. And as you can see at the beginning, CF is really high because of the huge gradient, because the inlet flow is uniform, and that's okay. But here you can see it's almost constant. So let's export this plot. Click on write to file, and now you can click on write, and in XY format you can have that. So CF dot XY. Okay, now, oops, where is it? Let me find it. It's here, flat plate backup, flat plate files, DPSF, FFF, Fluent, here. And you can always open it with Notepad++. And then you can copy this to the Excel file. Okay, you can play with these. So it's from the end to this. So let me sort it reverse and then copy and paste it. So it's X, it's CF from ANSYS Fluent. And let me delete this. We need it empty. We need this sheet empty. So this is CF exported from Fluent. Let's calculate CF from the formula, which is 0.664 over Reynolds number, local Reynolds number. So let's first calculate Reynolds X, which is rho X V divided by viscosity, and then CF 0.664 divided by SQRT of Reynolds X. The first one is okay because Reynolds is 0, so let me, for example, change it to this. It's not important, but after that you can see it's decreasing, and let's draw them. This way. And at the service name is CF, this is X, this is Y, and edit this def prompt point. So the first one is let's ignore the first one because the first node is okay. Let's ignore this. So ignore the first one. This is the right. And after that, you can see we have a good agreement. We have a good agreement between these. And that's it. You now you can see we have, uh, at least the flow field is correct. And this is a kind of validation, actually. So that's it. Let's go to Fluent, see some flow fields, contour, what happens. Okay, give me a minute. Oops. It is because of the internet. Okay, now it's fine, I think. Yeah. So sorry for that. Let's see the contour, velocity contour. See, this is the boundary layer, and it's really small compared to the height of the plate of the domain that we considered. So it's good. Let's see the temperature. Here you can see the heat transfer between the plate and the air, and you can see the evolution of the boundary layer. Wow, it's perfect. Let's check velocity vectors. Okay, near the wall especially. See, this is the boundary layer. Velocity is small, pretty small, and it increases. And after that, we have the free stream profile. So that's it. Now it is all, yeah, it's done for now. It's done. We are done for laminar flow. Let me save the project, and let's see what will go on and in the next session, which is about turbulent flow over flat plate. So I hope you enjoyed it. If so, please subscribe the channel. If you are new to the channel, please share these videos with your friends if you like them. Subscribe us, give us a thumbs up, and that's all I needed. That's all I need from you. And I hope these videos are, can help you in your studies, in your simulations, in your work. And I try to do my best. Thank you for watching this video, and see you in the next video. For now, bye bye.